It's definitely been far too long since the last Fatstacks vlog, and longer still since the start of this project, and if I'm not mistaken, I think this project has been active for almost 3 years now. I do want to apologize for that, of course. Part of the delay was the fact that the mods I use aren't being updated to newer versions of Minecraft. Part of it is also the fact that I was pouring time and mental energy into tasks that weren't really resulting in any real progress, and part of it was because I was just getting sidetracked by other things. But all of this resulted in the biggest reason for the delay. I simply just ran out of steam. Not to worry though, after taking a bit of a break and reevaluating what's been done and what needs to be done, I was able to get myself back on track and make some real headway here. The results, of course, is this. This is the final prototype of the Fatstacks project. It is everything that I've been planning and tinkering with finally coming together into one machine. Now this machine is 100% assembled, and its components have been tested individually, but the machine itself as a whole has not been tested in its entirety. But that's completely fine. It means that we basically have 2 or 3 things left to do, of course. One being finish the final prototype and work out all the kinks, and 2 is to take the information that I get from that final build and make the final version. We're nearing the end of this, which is great because this project has been getting a bit stale and I've been wanting to move on to something new. I figured it's time to wrap up this project and I want to wrap it up properly before I do something else, so I figured 2 videos ought to be just enough. So, changes since the last video. Obviously the biggest one is the machine is 100% complete and it has 100% of its components built and connected. From the execution pipeline to the state machine to the I/O, it's all here. The layout of the major components has changed too. I swapped the location of both the memory and the I/O. This is to keep the memory closer to the parts of the execution unit where it's needed most, but it also keeps the least significant bit of the I/O on the right hand side, which is ideal to me. Speaking of I/O, I mentioned in the previous vlog that I had a better way of controlling the buffer logic, and well, here I've actually implemented it. We have 2 rolling counters keeping track of where to read from and where to write to, and an up-down counter keeps track of how full the buffer actually is. There is still an issue with the users writing to the buffer and the computer reading from the buffer at the same time, but it should be an easy fix. Control pipeline has been rebuilt to stack up rather than out. This allows me to access all phases of the pipeline from any point with relative ease. And this is useful for things like forwarding logic, which needs to take a look at the write-back phase and other phases to see if data needs to be forwarded. The wiring at this point is a bit messy at the moment, and my hopes is to clean it up, but that will come later. That's all the major changes to the hardware, but the software has undergone some changes as well. I mentioned a while ago that I wanted to reflect the Stackish language as much as possible, and while there are some things involving ASCII that I simply cannot do, I can accurately perform all other functions. First change is my load immediate instructions are now all load 0 through 9 immediate respectively, rather than load 0 through 15. Part of the reason for this design change was, again, to more closely reflect Stackish, but it's also because I wanted to use the same ASCII characters Stackish uses for its instructions as opcodes for my instructions. So 0x30 through 0x39 was used to load immediate 0 through 9 respectively, but I couldn't include load immediate 0x0a because 0x3a was already used in the single in instruction. Load immediate string, of course, now works with infinitely long strings, but I covered that already in my last video. Conditional executes are all prefaced with 0x69, with the next character defining the condition, just like in the original Stackish language. The only difference, though, is the skip2 address must be defined in the 3rd byte. You may also notice that there are 2 out instructions, and that's because in Stackish one sends out the data as a character, and the other sends the data out as an integer. Again, I'd like to reflect the Stackish language as much as possible, so I included both, but they both behave the exact same way. On top of that, I've also double verified to the best of my ability that all instructions treat the data as they should, pushing to the pop stack when they're supposed to and such. You may have also noticed my odd choice in execution order for some of these microcodes, as well as various no-ops thrown in here and there. That is a really long and complicated explanation, but suffice it to say it's to make sure that the instructions work well with each other. Now, I had mentioned that the computer was 100% built, but not 100% tested. Truth be told, I had tested all of 2 instructions before encountering a problem, and unfortunately, due to the complexity of this computer, troubleshooting it was not going to be easy. So to aid in the challenge, I took a little bit of time to develop a basic logic analyzer. This is a very simple tool that should help me see what the computer is doing at any point in time, and thus should help me troubleshoot any issues that I may come across. That said, I'm not very good at troubleshooting and talking at the same time, so While I don't usually do voiceovers like this was the best way to communicate what was going on in my head without sounding like a babbling idiot. So, without further explanations, let's test this computer and see how we troubleshoot problems. Before beginning any troubleshooting procedure, it's always important to familiarize ourselves with the theory of operation. This isn't entirely necessary in our case because, well, I kind of designed and built this machine, I do know my way around it, but I'd like to review it for your benefit. As usual with most of my computers, the state machine controls everything, and its first order of business immediately after resetting is to reset the rest of the computer. After that, it can enter the fetch, decode, execute cycle. Now, fetch and decode are easy. In the fetch stage, the value in program memory is grabbed and stored in the program memory buffer, and the program counter is incremented. Decode, on the other hand, just gives the state machine time to decide what state to go to next. From there, the state machine goes down one of 32 paths, each one representing an instruction, and it begins executing the sequence associated with that instruction. Now, the sequence consists of microcodes and control codes. Microcodes get sent directly to the execution pipeline, while the control codes simply control what the computer is reading from and what data gets sent to the execution pipeline, which can either be the program memory, the random number generator, or the input buffer. While in the execution pipeline, additional data can be grabbed from the registers, operated on in the adder-subtractor circuit, and then stored in RAM, or RAM can be read and sent to the registers. This is of course a vast oversimplification, but it gets the idea across. The first instructions to test are the push immediate and push string instructions. No issues were encountered during these instructions, and they seem to be working fine. Running the following program, we can expect the stack to have 9 and the popped stack to have 5 and 4. If we run the program, we can see that the values are being stored correctly on the stack, but not on the popped stack. Now, if we take a look at the sequence described by the documentation, we can see that there's only 2 points in this instruction where we're actually writing to the popped stack, and that, of course, is in the add instruction. But you can see the sequence, of course, is 2 reads from memory and then 3 writes to memory. If we look at the logic analyzer, we can look for that particular sequence of events, and here we can actually see 2 reads and 3 writes. And we can see that the computer is reading from address 1, then address 0. This would make sense because we're reading stuff from the stack, and of course the stack is going to shrink down to 0 as it's read from. But then it writes to hex F8, hex 0, and then hex FF for some reason. The addresses being generated in regards to the pop stack are completely wrong. Now, it certainly is interesting that the stack addresses come out okay, but the popped addresses don't, because both of them go through the same circuit. The only real distinction between the two is the registers themselves. I'm not entirely certain where to start with this, but one thing that did catch my eye is the distance between the read popped stack pointer and the write pop stack pointer signals. Given just how much this signal has to go through before it actually makes its way back to the registers, you would expect the delay between these two signals to be a little bit longer than this. Because of this, my suspicion is that the value in the write back bus is getting written to the popped stack pointer before it has a chance to stabilize. Why this isn't the case for the stack pointer, I don't know, but I decided to set up a probe at the feedback bus and see what was going on. After generating another image with the logic analyzer, we can see very clearly here that the write signal is in fact coming into the register when the feedback bus is at its most unstable point. I remedied this by adding just a little bit of a delay to the write signal. This is a very hodgepodge solution and not one that I'm particularly fond of, but for the sake of getting this model up and running for the sake of testing, it'll have to do. Now, even after applying this fix, I was still getting some very interesting addresses, but that was because some blocks got stuck during the previous tests. Fixing this resolved the issue entirely. Running the following program, we can expect the stack to have 3 and the popped stack to have 9 and 6. The popped stack does have 9 and 6, but the stack has hex FA in it for some reason. Now, given that the last instruction we tested, which was the add instruction, worked quite well, and the subtract instruction is only slightly different from the add instruction, you would expect the rest of the circuits to behave properly. Of course, in this case, we can never assume these things, we just don't know until we test it. So, looking at the timing diagram generated from this run, we can see that the B input is in fact a 6 and the A input is a 9, but the result ends up being hex FA. Now, the first interesting thing to note, of course, is hex FA is the 2's complement of 6, so it appears we're actually seeing the result of 0 minus 6. So for some reason, the 9 on the A input is not getting through. Taking a closer look at the timing here, we can see that during T1, A is being read from, but T4 is also writing to A. It seems whatever's going on in T1 is requiring something from register A, but T4 D4 hasn't finished writing to that register yet, so whatever it's looking for isn't yet available. Normally during these kinds of circumstances we would have a forwarding circuit to actually forward the value from the write-back bus to wherever it's needed at that time. You can see here that I do in fact have some forwarding circuits. I've got one for memory and I've got one for the operations phase of the pipeline, but I don't actually have one for the registers themselves. This was a bit of an oversight. My assumption was of course that anything that goes into the registers at that point will be available, but I didn't take into consideration the fact that values are read from first, then written to. This means that a forwarding circuit needs to be added to this phase in the pipeline in order for this to work. I can make a note of that and of course implement the changes in the next revision, but for now we just need something to get this working. So a simple solution would be to just delay the write signal to the phase buffer. This way the value has time to be written to the A register and make its way to the input of the buffer before it's latched. And as you can see, that actually did help. You can see that 9 is being held on the bus for the duration of the operation, but the output is 1 rather than 3. I decided to manually set the inputs to see if I could replicate the issue. You can see here that when I set the A input to 9 and the B input to 6, the output is 3 as expected. However, by happy accident I discovered something interesting. If I set the value on the B bus first and then the value on the A bus, the adder behaves normally. But if the A bus was loaded first and then the B bus was loaded, the second bit of the adder would lock up for some reason. Something was holding state. Now this adder is not my own design and I'm not exactly familiar with its wiring or how it works, but that's quite alright. What I ended up doing was replicating the situation where the adder behaved normally and took note of what lines were on and what lines were off. Specifically, I took note of the signals that were involved with the carry between bits 1 and 2, and of course the signals in bit 2 itself. Once I had a good amount of notes, I replicated the situation where the adder was not working, and just compared the signals. After only a few short moments of looking, I discovered this right here. This torch was off despite not receiving any power. Or at least I thought it wasn't receiving any power until I took a look at the wiring for the carry-in circuit. It appears this repeater was accidentally powering that torch. Now why that torch didn't always turn off whenever there was a carry-in is unclear. It might have something to do with budding. Frankly, I don't care. I replaced the repeater with a couple torches and this resolved the issue. I also made a similar adjustment to the pointer register incrementer-decrementer circuit, since I figured it would probably have the same issue. After applying this fix, I tested the program again and it seemed to work just fine. And just to make sure, I also tested the add program again and that worked too. Now here we're testing two different branch instructions. The first one is execute if equal, and the other one is a direct jump. The program is simple. We're going to compare to see if 9 is equal to 6, and depending on whether that condition passes or fails, we're either going to execute the following loop, which is just a jump to itself, effectively stopping the computer at that point, or we're going to skip it and move on to the next loop, which also stops the computer at that point. Now we're expecting the condition to fail, of course, so we should see the computer get stuck in the second loop and not the first. And as you can see by the footage of actually running this program, we can see that the computer entered the first loop but didn't run it. It then entered the second loop, ran it once, and then entered the beginning of the program again. Let's take a look at the timing diagram and see what happened. Starting with the execute if equal instruction, state hex 18 is where the instruction actually decides if it's going to execute the following commands or jump to the skip to address. What should happen during hex 18 is the computer should not see a 0 flag and then move to state hex 19. Instead, the 0 flag was on at this point and the state machine moved on to state hex 1b. What's going on here? The way this was intended to work is when the state machine was in state hex 18, pipeline phase T2 was supposed to be executing microcode hex 30, which is the compare microcode. But here we can see that while the state machine is in state hex 18, microcode T2 was executing hex 1c, which is A to popped. In fact, if we look one clock cycle later, we can clearly see the hex 30 microcode being executed at this point. Adding a no-op state before state hex 18 should synchronize these signals, but it will require me to rebuild the state machine. Unfortunately, I have a tool to help with this. A while back, I had made a table building program, and I had asked people for help making the decoder side of the algorithm. A viewer by the name of Stenadion actually helped out with that tremendously. He ended up writing a very, very good algorithm that I've been using to this day to build my decoders. I'd like to say that I've been working to make this tool public, but truth be told, that project's been on the back burner for quite some time. Anyway, with the state machine built, I ran the test again. The program still doesn't work as intended, but we are making headway in the right direction. If we take a look at the new timing diagrams, programs, we can see that state hex 19, which was previously state hex 18, and microcode hex 30 in T2 are in sync. If I compare 9 to 6 and 6 to 9, the instruction behaves as expected. It skips the first loop and moves on to the second loop. Now, the loop is, of course, looping twice and restarting, but we'll get to that when we get to that. Interestingly enough, though, I may have spoken too soon about the instruction working, because if I compare 6 to 6, that ended up skipping the first loop too, when it should have actually executed it. If we take a look at the timing chart generated by the 6 equals 6 test, we can see that by the time state hex 19 is reached, and the state machine is ready to transition into the next state, the 0 flag is low and the negative flag is high. This should not be the case. We are expecting a 0 flag of 1 and a negative flag of 0. Something's missing here. If we take a look at that same test with some new probes, we can see that input A is 6 and input B is also 6 and subtract is on, but the output is hex 80. Something's wrong with the adder again. Apparently my carry in fix had a few side effects because it turns out that the carry isn't propagating all the way through the adder. I placed a repeater here making absolutely certain that there wouldn't be any side effects to this one, and that seemed to resolve the issue. This most likely won't be a problem with the address incrementer decrementer since the last bit is always statically set, but I applied the fix here too anyway. Now let's see if our execute instruction is finally working. During this test I noted two issues. The first issue is even though I made the adjustments to ensure a good comparison, the test still failed. The other issue that I noted is that the reset seemed to have started the computer in the wrong address. Regarding the second problem first, the reset sequence did go through the correct steps, though it appears resetting the program counter sends it to a random address, usually in the range of hex 30 to hex 3F. Since there's nothing there at this point, the computer just interprets that as another reset, and the computer resets again. I'll look into why that is in just a second. Regarding the first problem, however, the 0 flag is getting there, but it's late. I suspect that this is caused by the extremely long wire that the 0 flag has to go through in order to get from the adder to the state machine. This is a product of the prototype, and I don't expect this to be an issue in the final version. However, to get this model working long enough for me to do my tests, I decided to use command blocks to actually get the signal from the adder to the state machine. Looking at the timing diagram now, we can see that the 0 and negative flag both make it to the state machine with plenty of time to spare. But even so, the state machine still moves to state hex 1A, which is the skip sequence, instead of hex 1C, which is the execute sequence. The state machine might be at fault. I manually set the inputs of the state machine and checked the outputs, and those were correct. The other possibility is that the state machine's clock signal is coming in before the state machine has properly decided what state to transition to. Even though the flag signals are coming in with plenty of time, it still takes time for the state machine to actually decode that information and decide what state to transition to. I'll be sure to fix this in the final revision when I optimize the state machine, but for the time being I'm just going to fix it by slowing down the clock. I ran the test again and it looks like branching is working as intended, at least in the execute command. With the program comparing 6 to 6, it should succeed and execute the first loop, which it should never be able to exit, of course, and we can see that it does actually make it to the first loop, but unfortunately it ended up moving to the second loop anyway, which for some odd reason, succeeded. Let's take a look at the timing diagram and see if we can't figure out what happened. We can see here that the state machine enters state hex 1C, which is the beginning of the execute sequence, and latch program buffer goes high during this process. This of course loads the jump to address hex 07, but then it stays high for the duration of state hex 03, which is where the state machine is actually fetching the next instruction. This means that the program buffer held on to hex 07 during the process of fetching and decoding an instruction. The state machine decoded hex 07 looking for a valid instruction which it was unable to find, and ended up resetting as a result. And of course here's where things get really weird. The state machine begins the reset process, but then during state 1, instead of resetting the program counter is simply incremented, which caused the computer to run the next loop. There's more strange behavior happening in the reset sequence, and I need to address that at some point. But let me fix these issues first. Looking at the latch line for the program buffer, there should be a break in this between states. In fact, that's the way all of my latch and write lines behave, and I make sure they behave this way using a line called phi2. I suppose now is probably a good time to explain the clock method that I use for this entire computer. So my clock signal is actually 3 clock signals here. The first clock signal, simply called clock or state clock, dictates when the state machine transitions from one state to another. Phi1 is another clock signal that I have, and all that does is update the pipeline as well as enable all the read signals. Now the state clock and Phi1 are both in sync. Phi2 on the other hand lags behind Phi1 by almost 90 degrees. The idea here is that every time Phi1 rises, the read lines are updated, but the write lines are updated at the falling edge of Phi2. This ensures that the write signals aren't activated until about 3/4 of the way through the cycle. Normally I would just have the write lines be activated by by the falling edge of their respective write signal, but I've had problems with this design tactic in the past, and I've found that doing it this way is actually much easier. Anyway, the fact that the latch program buffer line remains high for 2 clock cycles means it probably wasn't connected to Phi 2. Adding an AND gate to this line and connecting that to Phi 2 seems to have fixed the issue, and the command seems to work just fine for both passing and failing conditions. Okay, so there's definitely something wrong with the way the computer handles resetting. Occasionally the address that it jumps to during the process of resetting isn't the one it's supposed to jump to. So I filled the program memory with a bunch of invalid instructions just to see how the computer would handle it. Theoretically, every time the computer encounters an invalid instruction, it should just reset and start at 0. But as this footage shows, resetting the program counter when there's an invalid instruction in the buffer loads whatever value is on that buffer into the program counter register. This should not be the case. This program counter register was designed to be resettable. So either I misunderstood it, or I built it wrong, or there's been a change in the way Redstone works and this no longer works as intended. I don't really care which at this point, I just need to get it working. So as a fix, I added a control buffer to the input bus, enabled that with the reset signal, and timed the reset signal going into the program counter with Phi 2. This seems to have resolved the issue. We can see that every time the computer encounters an invalid instruction, it resets and goes back to 0. Hopefully that's the end of that problem. Now we've already tested the execute if equal instruction, we still need to test the execute if not equal, greater than, and less than. Again, it's never a good idea to assume that just because one thing is working, they're all working. So I made another mock program to test the not equal condition, and gave it different sets of inputs to test both its skip sequence and its execute sequence. This seems to have worked just fine. Moving on to check greater than, however, I passed 9 in for the A input and 6 in for the B input, which means this should end up passing, but unfortunately it ends up failing. If we take a look at the timing diagram for this particular scenario, we can see that the state machine is clocked out of state hex 19. We can also see that the 0 flag is 0 and the negative flag is 1. However, if we look at the state table, we're looking for a 0 flag to be 0 and a negative flag to be 0. Now, 9 minus 6 is of course 3. This is neither 0 nor negative, so why the negative flag is on, I'm not sure. Double verifying the inputs on the state diagram, of course, we can see that 9 is in fact on the A input and 6 is on the B. The result of this subtraction is 3, but the flag is still negative. I recreated this situation manually and noted that the negative flag was in fact off, but if I fly over to the input of the state machine, we can see that this end is on. I believe what's going on is, as the numbers are being subtracted, there's a short pulse that's being generated on the negative flag. This pulse is long enough to activate the first command block, but not long enough to activate the torch on the other side of it, which means the other command block falls out of sync. I added a repeater to the input of this and set it on a 2-tick delay. This should lengthen any pulses that come in, and that seems to have resolved that issue. Again, this shouldn't be an issue in the final version. We're not going to be using any command block wires for that version. For the time being, this is just to get this to work. With this fix in place, the greater than condition skips and executes correctly. Likewise with the less than condition, this of course skips and executes correctly too. Now this program loads 5 onto the stack, then 1, and then jumps indirectly. The result should be a jump to address 1. However, when we run this, we end up jumping to address hex A. Looking at the timing diagram, we can look for the beginning of the indirect jump sequence by looking for state hex 1D. If we move forward just a little bit to the first read, we can see that T3 is executing the microcode hex 4B. This is a stack to counter, of course, so it makes sense that we're getting a memory read. And this is correct. Memory output, however, is hex A, which of course gets loaded into the program counter. Why was hex A in memory? Even more interesting, immediately after that memory read, T3 starts executing the microcode hex 4. There is no microcode hex 4. I mean, technically there is, but it's not valid. If we look at the way the microcodes are actually constructed, we can see that the first bit denotes the direction, 0 being register to memory and 1 being memory to register. The next 3 bits denote the register itself, and the final 3 bits denote the addressing mode for memory. Now, microcode hex 4, of course, is going to be a 0 for the first 4 bits. This means we're reading from register to memory, with the register being none, and 4 shows that we're sending that data to memory with the popped pointer as the reference, and of course with post incrementing. In other words, we're sending nothing to the popped stack. This is expected, of course. If we look at the instruction sequence in the documentation, we can see that we pull the value from the stack first, and then push that same value onto the popped stack. But the timing diagram shows that we're writing hex E to address 0. It should be writing 5 to address 0. And at the next memory write, it's writing hex A to address 1. It really didn't take long for me to realize what was going on. 9. It looks like I accidentally left a 9 on the A bus. You really gotta be careful where you leave these things. Upon fixing this, the instructions seem to have worked as intended. 5 gets pushed onto the stack, followed by a 1. And it even jumps to the correct address. Though if we take a look at what's being written in the popped stack, we can see that it's just writing a bunch of zeros. If we take a look at the timing diagram and go to the point where we would expect that write to happen, we can see that T3 is executing microcode hex 4 again. Where is this coming from? Well, I'd like to assume that it's the hardware's fault. In all honesty, I really should check the documentation first. If a mistake was made in the documentation, it could propagate all the way through into the hardware and cause problems. And it's a good thing I started here. If you look at the state table, you can see that the indirect jump sequence is sending a hex 4 by mistake. Now, fortunately, I made this in a spreadsheet, so it's easily fixed just by changing one value. And as far as I can tell, there aren't too many places where this is actually affected. So I ended up just rebuilding this by hand. There's no point in pulling out the table builder just for this small little mistake. I ran the tests again, and we can see the timing diagram for this too. The memory is being written to at the correct time with the correct address, but the value 0 is still being sent. I suspect this has something to do with the forwarding. The write-back bus is showing the correct values, but it's not being sent to memory. I created a probe to check the write-back memory signal, and ran another test. If we take a look at the timing diagram generated, we can see that the write-back memory channel doesn't show up. This means that there was no change and the renderer didn't bother drawing it. But this means something's wrong with the logic behind the circuit responsible for forwarding data to memory. Here are the expressions that I've used for all the control lines in each stage of the pipeline. If we look at the expression for the write-back memory signal, it's looking for a condition where the last cycle is memory to I/O, and the current cycle is I/O to memory. This, of course, forwards any value going to the I/O back to memory for pushing onto the popped stack, but this disregards any data going to the program counter. Here I'm manually patching that logic into the circuit. This is a real band-aid solution, and I'd like to try and come up with something a little bit more elegant, but for the time being this will work. And this seems to have fixed the issue. The computer is jumping to the correct address, and the correct values are being pushed onto the stack and the pop stack. The following program pushes 9 onto the stack, and then a 7, then executes 2 jump if equal instructions. The first, of course, is going to attempt to jump to 7, and the other is going to attempt to jump to 9. I also have 2 loops that address 7 and 9, each one pointing to themselves, so if the computer enters these loops, they get stuck. Given that 9 is at the bottom of the stack, we should expect the computer to jump into the loop at address 9 and get stuck there. If we run the program, we can see the first jump failed and the second jump succeeded, to be expected. But it ended up entering the loop at address 7 before going off in a totally random address and resetting. Looking at the timing diagram, we can see the state sequence where these instructions are executed, and we can see the 2 load immediates, of course, in the sequence, followed by 2 duplicate sequences. That particular state hex 3D, is the start of the duplicate sequence, which is not the instruction we're testing at the moment. Then the computer jumped to address 0, which it got from address hex 13. First issue, why is the computer going to state hex 3D? It should be going to state hex 24. Looking at the documentation, that seems to be fine. However, if I manually enter the input into the state machine, we can see that whilst it's in state 5 within input of hex 6B and the stack empty, the next state is state 3. Actually, I just realized state 5 is not the state I should be testing. I should be testing it in state 4. While in state 4 with the input hex 6B, regardless of the stack's empty status, the next state is always hex 3D. Taking a quick look at which lines are actually active on the state machine, you can see that lines 12 and 14 are active. If we take a look at the documentation, we can see that the result of having both lines 12 and 14 on means that hex 1D and hex 24 get sent to the output. These of course get ORed together, and this creates hex 3D. So this explains where hex 3D is coming from. Now the question is, why are both of these lines active at the same time, and which line should be active? We can see here that line 12 is part of the sequence that's responsible for handling an indirect jump, but line 14 is the one that's responsible for handling the sequence of a conditional indirect jump, or a jump if stack empty. So line 14 is the one that we want on. But this begs the question then, why are both of these lines on? We've already utilized line 12 before when we tested indirect jump. The fact that line 12 and only line 12 was on when we tested indirect jump, but now lines 12 and 14 are on when we're testing a conditional indirect jump, should give us a clue as to what's going on. If we look at the opcode that's used to decide these sequences, you can see that the opcode for an indirect jump and an opcode for a conditional indirect jump are virtually identical, differing only in the last bit. Now, given that both lines are active when this bit is a 1, but only line 12 is active when it's a 0, my guess is that line 12 is ignoring that bit. And if we take a look at the state machine in the game, of course, that is indeed what we find. At this point, I should probably confess that I'm not actually using the algorithm that Stenodyne created to make decoders. Well, technically I am, but the problem is it isn't updated to 1.15, so I actually did that myself, and I guess I screwed up the update. His algorithm works great, my recreation of it works terrible, so this isn't his fault, it's mine. Running the test again, we can see that the computer failed to jump on both occasions, so I'm guessing it's probably because the stack empty signal isn't making it to the state machine in time. However, according to the timing report generated by the logic analyzer, we can see that the stack empty signal never actually turns on. It took me a second to figure it out, but eventually I did actually realize it. I completely misunderstood what this instruction does. My assumption was that the jump if empty would actually pop something off the stack, so having two jump if empty instructions one after the other would pop values off the stack, and the last one would of course succeed. But this is not what the instruction does. All the instruction does is check to see if there's only one element in the stack, and then jumps to that address if that's the case. This means that I need to add a pop instruction between each jumps. Running this program, the computer does successfully jump, but then resets. The stack includes 9 and 7, and the pop stack includes 18 and 9. I'm really not sure where that 18 came from. Looking at the timing diagram again, it looks like pop isn't forwarding its value to memory. Again, it looks like the forwarding logic is ignoring registers A and B, so I'll be adding the band-aid solution again. Applying this fix resolved the issue. It looks like the stack is showing 9 and 7, and the pop stack is showing 7 and 9. However, the jump is still getting scrambled. I still need to troubleshoot that. First thing to note, the stack empty signal is on by the time the state machine enters hex 24. This is good. Second note is the state machine continues to state hex 28 before returning to state hex 3. This is what it's supposed to do. In fact, the previous instance of state hex 24 goes straight to state hex 03 just like it should. So the branching is working, and the correct sequence is being executed each time. Now, after the sequence from hex 24 to hex 28 is executed, a fetch is performed at address hex 05, which returns hex 0. Interestingly enough, the program counter gets written to at the very last second of state hex 03, right after hex 0 was already read. It also looks like it's attempting to write the value hex 9, which is what I was expecting it to write, as this is the address that it's supposed to jump to. So the jump to address is arriving at the program counter 1 clock cycle too late. This address should have already been written to the program counter by the time the state machine entered state hex 3. Looking at T4 verifies this. It's executing microcode hex 4B, which is stacked to counter, and this won't be complete until the end of the cycle, at which point program memory has already been read from. It looks like another no-op needs to be inserted into the sequence, which again means I need to rebuild the state machine. Inserting the no-op and rebuilding the state machine seems to have resolved the issue now. The program is behaving as it should, putting 9 and 7 into the stack and 7 and 9 into the popped stack, and jumping to address hex 9, where it gets stuck in a loop. Everything regarding this instruction seems to be working. Now, testing a random number generator is a little bit tricky. You can never tell if what you're getting is legitimately coming from the random number generator, or if it's something going wrong. So this program is going to test it by reading 3 random numbers. As you can see, the numbers hex 68, hex DC, and hex 70 gets pushed onto the stack. If we look at the timing diagram, we can look for when it starts to push these numbers by looking for state hex 2A, and we can see that these numbers appear in order. So here we can see hex 68, then hex DC, then hex 70. It looks like the random number generator is working, and the instruction responsible for reading it is doing its job. So here we have a program that pushes 4, 5, 6, and 7, but before pushing 7, pops the value and then unpops it. This is predominantly to test the instructions pop and unpop. And we already know that pop works, so this is really just to test unpop. The end result should be that 4, 5, 7, and 6 appear on the stack in that order, and when we run it, that's exactly what we see. So it looks like unpop is working just fine. Here we're waiting for an input, reading that input, storing it to the stack, and then sending it out to the screen. As far as the user interface is concerned, everything seems to be working fine. However, nothing is being pushed into the popped stack, and the stack keeps growing, even though we are supposed to be reading values from it. Now what should happen is when you execute the out instruction, it should read that value from the stack and send it to the output, and then read from the output and send it to the popped stack, forwarding the value of course. Looking at the timing diagram, when the state machine is in state hex 31, this is the beginning of the out instruction. Now if we look at T3 after this point, we can see that eventually it executes microcode hex 53, which is stacked to I/O, and 1 clock cycle later it's executing microcode hex 12, which is I/O to the stack. This should actually be the popped stack, which means I need to change all instances of microcode hex 12 to microcode hex 14, IO to popped. After applying this fix, I tested the machine again and noticed that the IO write system was sometimes getting stuck in a loop. This is of course a problem when the computer tries to read from IO while the player is writing to IO. This is something that I'll have to address later on, of course. But resolving the loop and applying this fix does seem to resolve the issue. The values on the input are still being forwarded to the screen, and the stack doesn't ever get past one element in length, while the pop stack grows every time an element is pushed to the screen. Testing the clear screen instruction, the first time I ran it, the screen didn't clear at all. It didn't take long for me to realize that I had actually forgotten to build the clear screen signal. After building the line, it appears that the clear screen instruction works just fine, and I do want to add that clearing the screen looks really cool. So here I've got a program that tests the in-all instruction. All it does is just read the input, of course, and then loop back to itself. And we're going to be testing that by writing to the IO the sequence 1 through 7. Now you would expect the numbers 1 through 7 to appear on the stack and then the instruction would stop. But here we're seeing 1 being written to the stack repeatedly and indefinitely. Now what should happen is the state machine should repeatedly send the microcode IO to stack out until it receives the not input ready signal. Now normally I would look to the timing diagram to get an idea of what's going on, but I have a suspicion. If we take a look at the wiring, we can see that there's no timing signal associated with the read IO line. While normally this is not a problem, the signal does need a break in order to update the pointer registers and the counter. It took a little bit of a trick, but by attaching these register update lines to the read line through an AND gate with phi2, I was able to give these update lines just enough of a break to update the registers properly. We can see here that 1 through 7 is being written into the stack, but as soon as 7 is reached, it doesn't stop. It continues to write zeros into the stack indefinitely. Taking a look at the IO's registers and pointers, they're all stopped in the correct point. So really the only thing to verify is the state machine. Now data is being brought in during state hex 34, and depending on the status of input ready, the next state is either going to be state hex 3 or state hex 34. Testing it manually, we can see that it's working correctly. If we take a look at the timing diagram again, we can see that the state machine enters state hex 34 just fine, but it remains in that state long after the last value from the IO buffer has been read. The only reasons the registers were kept from advancing is because of some failsafes I had put in the circuitry. It does eventually return to state hex 3, but long after the input ready signal comes in as a low. After that, it tries to execute again and fails as it should. I wasn't entirely certain what was going on, so I decided to observe the state machine as it was executing this instruction. What was interesting though is while observing it, it was working just fine. I even double verified this by putting command blocks on all of the write lines in memory. This way I can see exactly what lines in memory the computer's writing to and which ones it doesn't write to. And sure enough, it's working as intended. Now I noticed that the machine works when I was standing next to the state machine, but it wasn't working when I was standing next to RAM. What's likely happening here is when I'm standing next to RAM, the state machine is too far away to be properly updated by the game. I'm not an expert in core game mechanics, so I don't know for certain. But what I do know is that when I run this again while standing next to the memory, it fails to stop. And when I move back towards the state machine, it ends up getting right back on track. This is a problem I'll need to keep an eye on for now, but later when I rebuild this machine to take a smaller footprint, it shouldn't be an issue. As far as I'm concerned, however, the instruction is working. The program I've chosen to test swap top and bottom loads 1, 2, and 3 into the stack, then swaps the top and bottom. The expected result is the stack containing the values 3, 2, and 1 in that order, and that's exactly what we get. This instruction is working fine. To test the instruction swap top and second, I'm using a program that loads the sequence 1, 2, and 3 into the stack, and then swaps the top and second. The expected result is the stack containing the sequence 1, 3, and 2. And this is exactly what we get. This instruction is working as intended. To test the duplicate instruction, we are using a program that loads the number 1 into the stack and then duplicates twice. The expected result is 1, 1, 1 on the stack. And that's what we see happens. This instruction is working as intended too. And with that, that's all of the instructions tested and all the bugs worked out. Now there are still a few issues that I need to address, but some of them are just inherent flaws with this particular prototype and should be fixed when I rebuild it, and others are very small that I can easily address in maybe 5 minutes. The main thing here is I've finalized the functionality of the computer and collected some notes on what I need to change for the next revision. This is a great step in the right direction. I think what I'll do now is I'll get started on the polish work and I'll create the final revision, and once that's done I'll shoot a final video showing what's changed and how the final machine looks. With that said, I hope hope you enjoyed watching this video. This, of course, was a nice little update to the Fatstacks project, but it was also a nice peek into the crazy and maddening world of troubleshooting. And hopefully, at the very least, it was somewhat interesting. For the time being, though, that's all I've got. Thanks for watching, and I'll see you in the next video.